All right, so like I said, my voice is cutting in and out. It's in that in between, getting better, but
It's like you're
not. It's not gone, but it's not back yet. It's in a limbo.
Like a big it's like ha, JK.
You're like, okay.
that sounds really good.
Take a look at number 21. Number 21 says "just unlucky" is the title of the problem. It says one of the students in the introductory stats class in exercise 19 claimed to have tossed her coin 200 times. So she's repeating this 200 times. And she claims to have found 42% heads. It says, what do you think of this claim? So, does it seem like she got a reasonable response or an unreasonable response? So, if you were to flip the coin 10 times and you would only get 4 heads, does that seem pretty reasonable?
Yes.
Yes. But if you were to repeat that 1,000 times and you were to get 400 heads, the more times you do it, the closer you should get to 50%, right? So the question is, does this seem unreasonable based on the sample size? So this is p hat. Okay, p hat's 0.42. P hat is 0.42. That's what she got. That's not what should happen. That's what she got. So there's a couple of ways you can talk about what do you think about this claim. The first thing maybe to make note of is P, what should happen is 0.5. She should get heads 50% of the time.
That's recording. You sound like an 8th grade boy.
Yeah. I said I woke up this morning, I had more hair on my arms. Standard deviation of P hat
Practically you wasn't. It's recorded.
is the square root of PQ over N. So it's 0.5 times 0.5 over the N, which is 200. And if we were to calculate this,
0.0354.
okay, 0.0354.
0.0354. 0.
Okay, let me just type it in. But someone said that's what they got. So we divide this by 200, and then we square root that. 0.0354.
Yeah.
Oh,
How
I
they
said
say-
534.
Okay. So that's the standard deviation. Now there's 2 ways we can calculate whether or not they got a reasonable response. We can either A, find the 95% confidence interval and ask ourselves, did her result fall inside of that confidence interval? Or we can find the z-score and figure out if her z-score is more than positive or negative, what? 2. Because if the z-score is higher than negative 2, or I guess the absolute value of her z-score is more than negative 2, then that means she falls outside of the 95% confidence interval. Okay? So if you're actually just trying to find, if it's not asking you for a confidence interval, probably the quickest way would be to just find her z-score. So, I mean, method 1, I guess you could call it, to test the accuracy of her result, would be to find the z-score. The z-score is you take your data, which is what she got in this case, because we're not talking about numerical data, we're talking about categorical data, so proportions, minus the mean. The mean is what you should get. In this case, the mean is the population proportion, right? It's all the same concept. It's just the type of variable that we're dealing with. Divided by the standard deviation of our data, and our data is the p hat, or what she collected. So this is one way of doing it. Take 0.42 minus 0.5, divide by 0.0354. 0.42 minus 0.5 divided by 0.0354. We get negative 2.26. The absolute value of negative 2.26 is greater than 2. That means, remember, z-score is the number of standard deviations away from the mean. She is more than 2 standard deviations away from the mean. How much of the data should be within 2 standard deviations of the mean? 95%. So from this analysis, we can know that what she got falls outside of the 95% confidence interval. So does it seem like she got an unusual result?
Yes.
Yes. So her results are unusual. I mean, I don't know what her back of the book said.
I know.
I mean,
That's what it says.
technically, if you're using like a coin, it's more likely to land on tails because the head side is heavier because it uses more stuff on the head side.
It's 50-50.
Yeah, okay.
Yes, sir.
With the normal distribution, so if you're farther away, that means like you're,
Less likely to have her.
and then if you're in the middle, you're more likely. Oh, okay, that's what that means. All right, that's what I'm confused about. I think you're reading it as a graph.
It's weird. Because I got like a way more than I should have.
Okay, so method 2. Okay, so method 1 is using a z-score. Method 2 is using a 95% confidence interval. Inevitably, they're the same because the 95% confidence interval uses within 2 standard deviations, which is the z-score of a 95% confidence interval. So you're inevitably doing the same thing. But the formula for this is you take what you should have got, take away 2 standard deviations of p hat, and you take what you should have got and add 2 standard deviations of p hat. And the reason we do that is directly in the middle of a normal distribution curve is what should happen. If you go 2 below or 2 above, so this is -2 and 2, you should get a result somewhere in here. How often? 95% of the time. So that's what should happen. So you just want to see where does, based on this, where does ours fall? Well, we can also think about it as z-score. Where would -2.26 fall?
Like just right outside of the -2.
It falls outside the -2. So is it at our 95% confidence interval? No. So pictorially, that's what we can look at. But actually calculating this, we take what should happen and we minus 2 standard deviations. And remember, your standard deviation changes based on your sample size. And we take what should happen and we add 2 standard deviations. So we do 0.5 minus 2 times 0.0354. We get 0.4292. And then we repeat that same command, but we change this to a plus. And we get 0.5708. Now, remember, here's how you report a confidence interval. This is, I mean, you've got to remember all this stuff. Based on a sample of 200, right? And this confidence interval only deals with the sample size of 200. Based on a sample of 200, you can expect to flip heads between 42.9% and 57.08%. You can expect to flip heads between 42.9 and 57.08%. I forgot something here. Based on a sample of 200, we are 95% confident that we expect to flip heads between 42.9 and 57.08% of the time.
Dang.
There's a chance that this is wrong, okay? But 95% of the time, this is going to be right. So this will be right 19 out of 20 times, theoretically. That doesn't mean we're right all the time, but we're right 95% of the time, which means, or we're going to say we're 95% confident.
Oh yeah.
Now, since 0.42 is not an element of 0.4292, 0.5708, her results are unusual. It says the exact same thing. She got a result that's outside of what should happen 95% of the time. Right? We said 95% of the time we should get between 42.9% and 57.1%. Her result was not in that confidence interval. Therefore, we say her result's unusual. Okay? So another method of doing the same kind of problem. One with strict resistance. Now, of course, looking at this, all this here, compared to looking at the z-score, using the z-score is a lot quicker, easier way of doing that. But they inevitably tell you the same thing. It just depends on what the problem's asking you in terms of the context of how you attack the problem. So that's 21. I thought that was an important one to go over. 27 is important. 27 is an important one to make sure you know how to do it. Okay. It says a bank believes that 7% of the people who receive loans will not make payments on time. They're saying they believe that will happen. So that's going to be assumed as our population. That's our P. That's what they believe will happen. So P is 0.07. It says the bank has recently approved 200 loans. So we're going to be dealing with a sample size of 200. I'm not going to go over A and B separately. I want to go straight to C. Because A and B have to be completed in order to do C. So in doing C, you had to have already done A and B. But on a test, it's not going to give you questions that lead up to C. It's not going to give you, here's question A, here's question B, this leads up to question C. It's going to be a question. What's the probability that over 10% of these clients will not make timely payments? Okay. This is what we're testing. This is what we're wanting to check. So this is going to be our P hat. This is our P hat. This is what we're checking based on the claim. 7%. Now it's asking us to find a what? It's asking us to find a probability. Probability means we need a p-value. P-value means we need a z-score. Okay, this is the kind of things that you're processing in your mind. As soon as you see the word, find the percentile, find the proportion of, find the probability of, anything like that, you just come to mind. I need a p-value. In order to find a p-value, I need a z-score. We have a z-score for this kind of data. Let's draw a picture. Let's think about this first. If we were to draw this, it's a normal distribution. What's in the middle? P, which is what? 0.07. What should happen is directly in the middle. That's what we expect to happen. If everything goes right, we should get 0.07. They're asking 200 people. So in regards to 0.07, where is 0.1? Is it above or below? No, it isn't. It's above. All right, 0.1 is going to be somewhere over here. And it says, what's the probability that over 10%? So is that to the right or to the left? That's to the right. So we need to know the area of this region. We need to know the area of this region. Now, that means we're going to, what's our p-values in our chart tell us? Area to the what? Left. So we're going to need to know the area to the right of the negative z-score. Not negative 0.1, negative z-score. Because how far is 0.1 from 0.07? 0.03. So being above 10% is the same as being below 4%.
Yeah.
Does that make sense to everybody? The number of people that are above 10% is equal to the number of people that are below 4%. Because how far is 10% from 7%? 3%. So what's 3% below 7%? 4. So the number of people that make timely payments, more 10% of the people would be the same as the chances that less than 4% do not make timely payments. Okay? But it's not, the main thing is make sure you do not treat that as a negative 0.1. It's a negative z-score. So anyways, we got to have a z-score. In order for us to use the z-score, we need our data, which is our sample proportion, minus the what should happen, p, divided by the standard deviation. That's where part A comes into play. Because part A of this question says, what is the standard deviation of this data? What's the expected deviation of this data? Standard deviation of p hat is the square root of 0.07 times 0.93. 1 minus 0.07 is 0.93 divided by 200. Once again, guys, make sure you're following along with the calculator on this stuff. It's very easy to type this stuff in wrong. And if you type it in wrong, it will not give you the correct answer. We get 0.018. .018. Guys, I find it quite amusing that I stand up here in front of the room and I just make a comment. Make sure you're all typing this in the calculator, making sure you know how to get this, because if you type it in wrong, it's going to screw up your entire problem. And there's so many people in this room that take an initiative to care about their grade that half the class sit there anyway. Get your calculator out, type this crap in. Or 11 weeks in the school year, you should be having a calculator sitting on your desk as soon as you walk into the class on a daily basis. Assume you're going to need a calculator every day. Calculate this z-score. 0.1 minus 0.07 divided by 0.018. 0.1 minus 0.07 equals divided by 0.018. We get a z-score of 1.67. If we want to know the area to the right of a z-score of 1.67, that's the same as the area to the left of negative 1.67. So to find the area to the right of 1.67, we need the p-value for the z-score negative 1.67. That's directly in our chart. We get a negative 1.6, go over to 7, and you should have 0.0475. Right? I'm using a different chart than what you guys have. Maybe. No, it's the same chart. Sometimes if you lose this chart and you print another one off the internet, sometimes the numbers will differ by a 10,000th of a decimal. Okay, just because it depends on the company that's made the book. They vary slightly. So, the probability of being below negative 1.67 standard deviations below the mean is 4.75%, which is going to correspond to the exact same probability of being more than 10% or above 10% of the clients making time payments. So, and that should be the answer in the back of the book. 4.8? Okay, so approximately 4.8%. The probability that over 10% of their clients will not make timely payments is approximately 0.048, or you could say 4.8% of the time. You can expect that more than 10% of the clients will not make timely payments. JJ, you have a question?
Wait, where did you get that 0.0475?
We went to the p-value chart, and we found we had a z-score. We needed the p-value for the z-score negative 1.67, and so we just go to the negative 1.6.
Excuse the interruption, but when
7.
the base grade dismisses, they need to report to the ground room for our presentation today. 7th grade will need to report there from lunch.
Okay. So, next important question is 31. 31 is an important question. 31 is a school district says, based on the 74% national retention rate, does the college where 522 of 603 freshmen return the next year, sophomores, have the right to brag that it's unusually high retention rate? So retention rate is the percent of students who return after their freshman year of college. So if you got a 74% retention rate, that means 26% of your students dropped out after the first year of high school. Now, we don't have to collect just samples. This college is collecting a sample, but in terms of the college, they have 603 students. That's all of their students. Does that make sense? It's a sample of the entire nation, but it's all of their students. if they look at all of their students, they can make a claim of, hey, we seem to be doing better or worse than the entire nation. Does that make sense? But if the national rate is 74% and they come up with a result at 76%, does that mean that necessarily they're doing any better? Not necessarily. It's dependent upon the standard deviation. Okay? Now, even if they were to have an 80% retention rate, depending on their sample size, 80% retention rate, even though it's higher than 74, might not really be better. Okay? It's all about, does their results fall within the 95% confidence interval of what should happen? If their results fall within it, then that means that they're not really any different than anyone else. But if they're above or below, abnormally above or abnormally below, they either have the right to brag or they have something to worry about. Does that make sense to everybody? They're either way too easy and they've got a higher retention rate, or they're way too hard, or they've got something motivating the students to come back, or there's something going on that's causing too many of their students to drop out. So, when we say, based on the 74% national retention rate, that's our P. Colleges should expect a 74% retention rate, which means that they should expect after the first year for 1/4, 25% of their students to drop out. Let's just expect it. I mean, that's a pretty general rule of thumb. I think the retention rate is actually from the first semester of college to the second semester is even lower than this. I think it's only like 67%. Like a third of the students drop out of college the first semester of college. Okay, it's just that's what it is. Does a college a college where 522 of the 603, so theirs is a proportion. Also, they give it to you as a proportion. So we can find p hat by just taking 522 and dividing by 603. I have notes all day today. And my voice is so quite a comical YouTube videos.
They should have some P's now.
That's true. All this math.
We're doing steak.
Alright, so p hat is 0.866, 0.8656, or 0.866. So the national report is 74% retention rate. They've got an 86.6% retention rate. So they only got 13% of their students. So that is higher, but is it abnormally high enough to determine if they are better? So we can do it two ways. What should be in the middle?
0.74.
0.74. Now 0.866 is definitely higher. Okay, it's definitely higher. So it's definitely above. But the question is, if we were to go to -2 up to +2, if we were to look at the confidence interval, does 0.866 seem to be enough that it falls outside of the confidence interval? So there's two ways you can do this. You can create a confidence interval and ask yourself, do they seem to fall inside the confidence interval? Or you can just calculate their z-score and ask yourself, does the absolute value of their z-score seem to be more than 2? Either method. It's just like the first one we did. So I'm going to do the z-score method because it's quicker. So the z-score method. I'm going to calculate their z-score. You take what they got minus what's expected to happen divided by the standard deviation of their data. And the standard deviation of their data is always dependent upon the sample size of people that they asked. So the standard deviation of their data, that's the square root of 0.74 times 0.26 divided by what? 603.
Oh, okay.
Because how many people is in their sample? There's 603 people in their sample. So we did 0.74 times 0.26 divided by 603 gives us 0.0179.
So that's like step one if you're wanting to find the z-score method, right?
Yeah, but if you want to think of the steps.
Have to think of it as steps.
You need to think of it as, here's my formula for z. What's it take for me to figure out z? And so we know what p hat is, right?
Yeah.
Check. We know what p is. Check. We need to know standard deviation of p hat. We don't know that. That's what tells us to jump over and do that.
But yeah, but if we didn't have a different thing of that, we wouldn't be using.
If we didn't have what?
Like if we didn't have. Like does it always go straight to the standard deviation? Like we have to find
Unless it's given to you. And sometimes the standard deviation
And
can't
then,
be
yeah,
given to
you
you,
just
and then you
go.
just plug it in. So that's the reason it's better off to just check. Do I have what I need? Okay, I don't have this. I need to find this. So we plug it in. We get what we got minus what we should have gotten divided by the standard deviation. John, 7.
20.
Okay, so 7.086.
39. 39.
So 7.04, right?
Yeah.
Okay. Alright.
Few lessons.
7.04. Now, our standard, or our 95% confidence interval only goes up to 2 and down to -2. Is 7 within that?
No.
No, it's extremely far out there. So, do they have the right to brag?
Yes.
Yes. Okay. The absolute value of 7.04 is greater than 2. That means that 95% of the time, if you have a sample of 603 students, you should be between A and B. They're definitely outside of that interval because their Z-score is a lot higher than 2. Therefore, yes, they have the right to brag. That's just like when the OGT results come back, and it's like West Union got a 76 in math, People's got a 78 in math, and North Adams got a 79 in math. Although they seem like North Adams did the best, it really, you can't look at just the pass-fail rate to know who really did better. Because the 76 and 78 and 79 in Evansville are probably about the same score. So, just if you look at just the raw data, it doesn't tell you.
What was the 2 from again?
Because the empirical rule says 95% of the time we should be within 2 standard deviations. And 7.04 is greater than 2. So it's more than 2 standard deviations away. The empirical rule says 95% of the time. 95% of the time. P hat will be within 2 standard deviations of P. How far is P hat in terms of Z-scores? How many standard deviations is P hat away from P in this example? It's 7 standard deviations away. The empirical rule says 95% of the time, P hat should be within 2 standard deviations. So we've got an example that's 7 standard deviations away. That's abnormally large.
This is starting to come together. I really like this right now. I feel a lot better.
Does that make sense?
This is
Literally
helping.
12 minutes ago, I was like, oh my gosh, I'm gonna fail, and I'm not going to college, I'm not going to just like these people, and now I'm like, yeah, I'm like Einstein. Einstein actually
And then
knew
a
about
week
school.
will be freaking out
Didn't
again,
sound like
so.
Yeah, you talk to his
Okay.
I'm still freaking out.
So was the second method the one
six
that I
projects.
did talk to the age of
Okay,
6 months?
so the second method is where you would actually create the count. So, I mean, if you, I can show the
You don't
95%.
have, I was just,
Yeah, I can show it real quick. It's whichever method you want. 95% confidence interval. You do P hat, and then not P hat. You do P
Plus 2.
minus 2 standard deviations.
Okay,
I
so
see
you
you
want
want
to
to
do
mix
mix
up
up
and then end up doing one giant big method of Sarah, like a Sarah method, and end up screwing it up.
No, we gotta do P take away 2 standard deviations. If we take P and we subtract 2 standard deviations, that's gonna tell us the bottom number in our confidence interval. Our smallest value to still be inside this range window of values. If we add 2 standard deviations, that's going to tell us where this line is. So 95% of the time, we should get a result that's between these 2. So that's what this is doing. So we're going to do 0.74 minus 2, 0.0179, 0.74 plus 2 of those. .74 minus 2, 0.0179. Second entry, change it to plus sign. So we get 0.7042, 0.7758. So the way we report this is 95% of the time, or we are 95% confident. Either one, they mean the same thing. 95% of the time, or we are 95% confident. 95% of the time, a sample of, because remember, our confidence interval is dependent upon the sample that we're dealing with. So this confidence interval only deals with a sample of 603. It does not apply to a sample of 500. Okay, so 95% of the time, a sample of 603 will result in a retention rate between 70.4 and 77.6%. That's how you can interpret that confidence interval. 95% of the time, if you were to ask 603, if you go to a college and you're sample 603 of their sophomores, to figure out how many of them stayed from their senior year and how many of them dropped out, you should find that between 70.4 and 77.6% of them stayed for their sophomore year. Okay? Now, what was the retention rate of this school?
Does anyone else hear that?
I don't hear anything.
I hear someone playing heavy metal rock.
This school's retention rate.
I don't hear it.
This school's retention rate is 86.6%. We just said 95% of the time we should get a result of this. Are they better than this?
Yeah.
Yes,
Yeah.
they're way better. They have a right to brag. If they had a retention rate of 77.7, even if it's just 0.1% better, they have the right to brag because they're falling outside of that. What should happen 95% of the time? They're in that only that 2.5% chance of possibility.
So if it said 0.7759,
If this said 77.59 and they had a retention rate of 77.6, if they even had a retention rate of 77.591, it doesn't matter. If they're slightly bigger, they get the benefit of the doubt. Because that means that they're in that 2.5% that a possibility. Because remember, 95 is in the middle, there's 2.5 on each end. So they're in that 2.5% window of this should only happen 2.5% of the time. So they're in that very limited window of should happen.
Wow.
Okay, so that's 31. That's an important one to know. Another one that's kind of common is number 35.
could you actually figure out the number of people that would drop out using that? So like,
You can make a prediction.
603, so therefore
You can make a prediction, yeah.
70.
So you could say between 70.42 and 77.6 will, so just do 70.42 of 603 and 77.6 of 603. And then that can give you a window of actual people.
Yeah.
So between this many people should be retained, between 400 and 482 people
Alright.
should stay. Yeah, you can actually just take the percentages and take your sample size and convert that into hard numbers, back into hard numbers.
Should they do proportions for middle schools and true?
Do what now?
Should we get like proportions for middle schools, like schools that have larger than 600?
Yeah. Could you use that to predict other schools? Yeah, it would just be whatever school that you're interested in. You just have to make sure if you wanted to use that kind of result, you have to use a sample of 603. Because that result only pertains to 603
Yeah,
students.
so it is sometimes.
Yeah. As long as you meet your conditions, as long as you do independent random, which if you ask every single student in the school, you don't have to worry about that because you're not just doing a sample, you're doing everybody. So you don't have to worry about that. If you don't do more than 10% of the entire United States of college students, which if you ask just one college, that's not going to happen. And if you do 10 successes, 10 failures, if you ask an entire class, say 200 people, even a 10% retention rate is 20 people. You know what I mean? So you're definitely going to meet that 10 people success, 10 people fail rule. So you can always do that, no matter how. The only thing you couldn't do like you're not going to find a college that only has 20 students in a class. But yeah.
Are you gonna give us a new P value thing for the test?
Possibly.
Cause I don't wanna like highlight on mine and then like. not
Yeah, you
use
told
it.
us that we'd use it on every test. This was our key.
Well, I wanted to
So-
make sure no one used it as
Yeah, I
a
put notes.
note card.
Yeah, I did.
So, 35 is titled Gaydar. Hey, this is actually a popular study that's been done several times. Exercise 7 in chapter 1 described a study that showed that heterosexual women during ovulation were significantly better at correctly identifying the sexual orientation of a man from a photograph of his face. They actually did this study on Mythbusters.
Yeah.
They did a Gaydar study on Mythbusters. And then it's just like they did the beer goggle study, where they would drink and then they would rate the looks of the women, yeah, or the men, and then they drink more and then they compare did they see drinking more alcohol caused them? And it's been studied. It's a study that's been done a bunch of times. Yeah, but yeah, it always seems to work out. In other words, ovulation improves a woman's gaydar. Near ovulation, on average, women correctly identified the orientation of about 65% of the 100 men shown. If this is the probability of correctly identifying the orientation of a man, what's the probability that a woman would correctly classify 80 or more? So 2 of the women in the study did this. They classified 80 or more. They had a really extreme high accuracy rate. So what's the probability of that happening? So P,
Is it 80?
we should, it says near ovulation on average, that's what should happen, 0.65. Okay, these women, it says what's the probability, so probability, it means we're looking for a p-value, so probability of predicting, what is it, more than 80% of the time, more than 80, correct? Okay, P is probability. Probability means we need a p-value. P-value means we need a z-score. That's what should be coming to mind when you read this problem. That's what should mentally be going on. Probability, I need a p-value. P-value means I need a z-score. Z-score means I need this formula. Because we're dealing with proportions. So we need our proportion, what we got minus what we should have got, divided by the standard deviation. Okay, it's interested on her being correct 80 or more times. So our p-hat, our cutoff raw score, is going to be 80 or more. So we're interested in 80 out of what? 100. So 0.8. So look what we have now. We have our what we should get, check. We have what would happen in this woman's case, check. We need the standard deviation.
No, you need
So we use the standard deviation formula. The square root of 0.65 and 0.35 over 100. Okay, if there's a 65% chance of success, the chance of failure would be 35%. Remember, Q is always 1 minus P. So if you do 1 minus 0.65, you get 0.35.
0.0477.
0.0477. So I'm doing the z-score method, okay? Because it's asking for a probability. Now it doesn't say is this a likely occurrence. It's saying what's the probability of this occurring. Does that make sense to everybody? If this said is this a likely occurrence, you wouldn't need to find the probability. You just find that the z-score is more than 2. Okay, if it's more than 2, you say this is an unlikely occurrence. So we take 0.8, we subtract 0.65, we divide by 0.0477. Anybody have that?
3.144.
Okay, so is this a likely occurrence? No, because 3.14 is more than 2 standard deviations away from the mean.
That's high.
It is kind of ironic, isn't it? Okay, so let's think about this. This is 0.65. This is 0.65, which has a z-score of what?
0.
0. We're talking about having a z-score of 3.14,
It's more than
and it wants to know the probability of predicting more than that 80% of the time. We want the area to the right. So in order to find the area to the right, we have to use the p-value of the negative z-score. So we've got to know the p-value of the negative z-score of negative 3.14. Is that even on our chart? Yeah.
What would happen if it wasn't on our chart?
Okay, that's a good question. So let's get through this one and I'll show you.
Okay, sorry.
That's all right. No, that's okay. So the probability of predicting more than 80 is 0.0008 or 0.08%. Or what makes more sense than this is 8 out of 10,000. Chances of this occurring, you have to ask 10,000 women, and only 8 of them would this happen with. Okay, because if you think about it, this is tens, hundreds, thousands, 10,000s. So I'm just converting this decimal to a fraction. Because 8 over 10,000s makes more sense than 0.0008 or 0.08%. This is kind of, people can read this and make numerically more sense out of it than a percent.
So if it would have been like 0.0016, would it then be 16 out of
.0016 would be 16. .0016 out of 10,000.
When would it change to 1,000?
If there was only 3 numbers.
So like 0, 1, 6 would be 16 out of 1,000.
Yes. Yes. You just count. So it's hundreds, thousands, 10,000s. The last number tells you what goes in the bottom. So the question was, what if the p-value is, so this isn't something that's in this problem, but what if z is less than negative 3.49 or z is more than 3.49? Our chart doesn't cover these two, right? I got one problem that had a z-score of 7. Our chart doesn't cover a z-score of 7. It only goes up to 3.49. If you're talking about the p-value for something that is less than negative 3.49, you just repeat it as, you report it as 0.0001. You just say it's less than 0.0001. That's how you report it. You don't actually give a number. You just say it's less than this number. Does that make sense? It doesn't happen that often. If the z-score is greater than 0.9, you would say the z-score, the p-value for a z-score greater than 3.9 is greater than 0.9999.
Wait, so are those the two last or first on the P chart?
Yes, that's the lowest and the highest. So on that problem, the previous problem that we were looking at, that the chances of it occurring for that college was 7, right? The z-score was 7. The chances of that occurring, or the chances of getting something more than that, which would mean less than negative 7.04, right? Would be the chances of that happening is less than 0.0001. So the chances of this happening is less than 1 out of 10,000 tries. Because that's more than 3.49.
But if it was less than 3 point.
Well, remember, we're talking about area to the right.
Yeah, but why did you do less than 0.0 blah, 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 and why did you do more than 0.9999?
Well, because if we're talking about the college having a retention rate higher than 86.6%.
Which is
So you can also report it as the chances that a college has a retention rate less than 86%, 86.6% is more than 0.9999. But the chances that a college is better than that is 0.0001. It depends on the context of how you're analyzing or how you're interpreting it. Alright. See you guys tomorrow. Tomorrow's back to notes. Finishing up this section.